Okay, so let us do some more numericals of rigid body dynamics. Here, this problem, see this problem, okay. A sphere of mass m and radius r slips on a rough horizontal surface at some instant of time. It has translational velocity v0 and rotational velocity about the center of mass is v0 by 2r. When the sphere starts pure rolling, find translational velocity of the sphere. Okay, so how to do this problem? First, see this sphere. The center of mass has a velocity v0 and it has an angular velocity v0 by 2r. It is r. So the bottommost point will have a translational velocity v0 as well as in the forward direction, as well as a velocity omega 0 r, that is v0 by 2 in the backward direction. So clearly v0 is greater than omega 0 r. So it is a case of forward slip, right? So when it slips forward, friction acts backward. Okay, so now let us write the equations. Okay, so for forward slip, first let us write the equation of motion. So F equals ma. Okay, so this is the equation of motion for translation of center of mass, and for rotation about center of mass it will be tau equals I alpha. Now friction creates the torque, so torque is Fr about center of mass, and I, this is a solid sphere, this is 2 by 5 mr square alpha. So F is 2 by 5 mr alpha. So now put this thing here, so I get ma equals 2 by 5 mr alpha. So m cancels out, I get r alpha equals 5a by 2. Okay, so now write the kinematical equations. Okay, so what will be the kinematical equations? For forward slip there is translational retardation. So suppose after a time t, when it starts pure rolling, then the velocity becomes v and the angular velocity becomes omega. So now as it starts pure rolling, so this is v, the bottommost point, and this becomes omega r. So for pure rolling, v equals omega r. Now this is the condition of pure rolling after a time t. Okay, so we will write v equals v0 minus at. Okay, and we will write angular acceleration. So it will be omega equals omega 0 plus alpha t. So it will be, if I multiply both sides by r, it becomes omega 0 r plus alpha r t. So omega r equals v, omega 0 r equals v0 by 2 plus alpha r means 5a by 2 into t. Now from here at is v0 minus v. Now put this value here. Okay, so we will get v equals v0 by 2 plus 5 by 2 v0 minus v. Okay, so it will be v plus 5v by 2 equals v0 by 2 plus 5v0 by 2. So it becomes 3v0. So 7v by 2 is 3v0. So v is 6v0 by 7. Okay, so this is the answer. When the sphere starts pure rolling, so the velocity of center of mass is 6v0 by 7. Okay. Now let's do the next problem. See the problem. Find the final velocity of center of mass when it starts pure rolling, and the distance covered when it starts pure rolling. Okay, so how to do this problem? So suppose this sphere was rotating with omega 0, but it was not translating because no surface was there. So that's this velocity was 0 initially. Okay, so the bottommost point it was 0 and this was omega 0 r, say. Okay, let's call it omega 0, it will be convenient. Okay, this is omega 0. Okay, initially. So clearly here v0 is less than omega 0 r, so it will be a case of backward slip. So for backward slip, friction acts forward. So let's write the equation of motion first. Similarly, as we have written earlier, F equals ma. F is mu n, ma. Now n is mg. So we get A equals mu g. And then write the equation of motion for rotation about center of mass. Tau is I alpha. So Fr about center of mass torque produced by the frictional force is 2 by 5 mr square alpha. So it will be F equals 2 by 5 mr alpha. So now F equals ma we know. So 2 by 5 mr alpha. So A becomes, rather write 5 r alpha becomes 5a by 2. Now here, suppose after time t, this starts pure rolling. So its velocity becomes v, translational velocity of center of mass, and angular velocity of about center of mass becomes omega. Okay, so here it is v and omega r, they will be equal for pure rolling. Okay, after a time t. So we will write back in backward slip, we know it is translational acceleration. So v is 0 plus at and angular retardation. So omega is omega 0 minus alpha t. So omega r is omega 0 r minus alpha t. So it is v equals omega 0 r minus alpha r is 5a by 2 t. Now at equals v. So I can put here v equals omega 0 r minus 5v by 2. So if it comes this side, then it becomes 7v by 2 is omega 0 r. So from here we can write v equals 2 omega 0 r by 7. Okay, the first answer is here. When it starts pure rolling, the velocity of center of mass I have found. Okay. Now the distance it covers before it starts pure rolling. How to find the distance? It's easy. It's v square equals 0 square plus 2as. Okay. So we can write s equals v square by 2a. So it will be v I have already got, so it will be 1 by 2. Acha, a is mu g, right? So put mu g, and v square is 4 omega 0 square r square by 49. Okay, so the displacement is 2 by 49 omega 0 square r square by mu g. Okay, so it becomes like this. Alright, now let's move to the third problem. Okay, this is also a problem of ruling. Now a disk is given. The previous two problems were solid spheres. Now it's a disk. Velocity of center of mass at t equals t0 when it starts pure rolling. Then coefficient of friction is mu, so calculate t0, the time after which it starts pure rolling, and calculate work done by frictional force. So how to do this one? So here initially it was having a pure sliding motion, that means the velocity was v0, velocity of center of mass, but it was not rotating, so it was omega 0 was 0. So it is v0 and this is omega 0 r, this is 0. So clearly v0 is greater than omega 0 r. Okay, so this is a forward slip. So friction acts backward. Okay, so now write the kinematical equations first. In forward slip, it is after time t0 it acquires pure rolling, so it becomes v and becomes omega. So v equals omega r for the bottommost point. Okay, pure rolling. So after time t0 it becomes v equals v0 minus at, and so let's write at first. At will be v0 minus v, and translational and angular acceleration, translational retardation, angular acceleration, so omega will be 0 plus alpha t, so omega equals alpha t, right? So omega r equals alpha r t, so omega r is v, that is alpha r t. Okay, now write the equation of motion. So f equals ma and tau equals I alpha. So tau is fr, is now for disk it is half mr square alpha. Now f becomes half mr alpha. So here half m r alpha equals ma, so cancel m, so r alpha becomes 2a. Okay, so v here becomes 2a t. Okay, now you put the value of at from here. Okay, so v equals 2 v0 minus v, so you get 3v equals 2v0, so v is 2v0 by 3. So the first answer comes. When it starts pure rolling, the velocity of center of mass v is given by 2v0 by 3. Now what is the time? It's very simple to have the time from this relation. Okay, from this relation, so t equals, or t0 rather, they say it is t0. Okay, put it t0. So t0 is v by 2a. Now a is mu g, we have done it in the previous problem also, so it is 2 mu g. Now put the value of v, it is 2v0 by 3 by 2 mu g, so it will be t0 is v0 by 3 mu g. So this is the time after which the disk starts pure rolling. Okay, fine. Now what is the work done by the frictional force? Okay, So we know work energy theorem. The work done will be the change in kinetic energy. Okay. So initially the kinetic energy was purely translational. So it was half m v0 square. But then it starts pure rolling at the end. So it will become half m v square plus half I omega square, right? Now see, it is half m v0 square minus half m v square plus half m r square omega square. Now r square omega square is v square, right? So it will be half m v0 square minus half m v square plus 1 by 4 mv square. So it will become half m v0 square minus 3 by 4 mv square. So now put the value of v. V is 2v0 by 3, so it will be 4v0 square by 9. So 4 and 4 cancel, 3 and 9 cancel, it is 3. So work done is half m v0 square minus 1 by 3 m v0 square. So it is 1 by 6 m v0 square. So this is the work done by friction, the third answer. Alright. Okay. Now let's do next problem. A solid disc and a ring, both of radius r and mass m, means identical, placed on horizontal table simultaneously with some angular velocity omega 0. Which of the two will start to roll earlier? Okay, coefficient of friction is mu k. Okay, you can do it. Find the time in general. The time for starts. They had the same angular velocity. Okay, so they were rotating. They had pure rotational motion. No translational motion was there, right? So right. It will be a case of backward slip, clearly. So we'll have forward friction, that means forward translational acceleration and angular retardation, right? So V will be equals AT, okay, and omega will be omega 0 minus alpha t. So omega r will be omega 0 r minus alpha t. So it will have V equals omega 0 r minus alpha t. Okay. Okay. Now, because when pure rolling starts, V equals omega r. Alright. Now, first we have to calculate t. We have to calculate V, then we can calculate T. Okay, so now you just write this thing. We are doing it in general, mind it. So F equals ma and tau equals I alpha. So here Fr equals I alpha. So we will have F equals ma, right? So put it here. We'll get MAR equals I alpha. So alpha R will be MAR square by I, multiplying both sides by R. Okay, so it will be V will be omega 0 R minus MA r square by I into t. Alright. Yes. Okay. So we will have now AT equals V, right? So in place of AT we can write V. Okay, this AT we can write V. Okay, so V will be omega 0 r minus m r square by I into V. So we will have V as omega 0 r divided by 1 plus m r square by I. Okay, alright. So now as I have calculated V, we will have T very easily. T will be V by A. Now A is mu G, so it is V by mu kg. Okay, so just we will replace the value of V and we will get T. Omega 0 r by mu kg 1 plus m r square by I. So this is the time. Okay, in general we have found it. Now you write for the ring, it will be, for the ring I is m r square. Okay, so it will be, T will be omega 0 r by 2 mu kg. Okay, and for the disk it will be, I is half m r square. So you have T as in from this equation. Okay, both of them from this equation. Ring in place of I have placed m r square. For disk I am putting half m r square. So it will be 1 by 2, that is 3, omega 0 r by 3 mu kg. Okay, so it's very clear that which one is, for the ring let's call it T1 and for this let's call it T2. Which one is smaller? It is 3, it is 2. So here the denominator is bigger, so it is T2 is smaller than T1. So disk will start to roll earlier. Okay, fine. Do the next problem. A small sphere rolls down without slipping from the top of a track in a vertical plane. As an elevated section or horizontal part. The figure is not given here. The part is 1 meter above the ground. The top of the track is this. The distance on the ground with respect to point O, which is vertically below the point A of the track where the sphere lands. Okay. See, it is like this. The track is like this ground. Okay, so this is 2.4 meter. Okay, and this is 1 meter. Okay, the sphere is rolling down here from here to here. Okay, then it falls on the ground like this. Okay, so they have asked you this distance x. So it is the case of horizontal projectile, right? Okay, so what you need to do is to find this velocity v. Okay, so it's just conserve the mechanical energy and get it. Okay, so here on these 2 points, suppose this point is A and this is B, call it. So conserving mechanical energy, what you will write? EA equals EB. So what is EA? it is mgha, the gravitational potential energy, and the kinetic energy is 0, it is at rest. Now what is eb? It is mghb, gravitational potential energy, plus now the kinetic energy will be the rolling energy. Remember, this sphere is not sliding, it is rolling. The rolling energy is given by half mv square plus half I omega square. So it is, call it a solid sphere now. So it will be mg ha minus hb. It will be half mv square plus half 2 by 5 mr square omega square. So v equals omega r for pure rolling, we know. So we'll have this v square, 2 and 2 gone. So we will have m cancels. We have g minus 1, v square by 2 plus 1 by 5 v square. So it will be 10, 5 plus 2, 7 by 10 v square. Okay. So it will be v square is becoming 10 by 7 into g into 1.4. So it is 2g, isn't it? 14, 7, 2g. Okay. So now we have to find x. So for horizontal projectile we know what is x. X is vt. Now what is t? Root over 2hb by g. Okay. So we will have root over 2 v square hb by g. So it will be 2 into 2g into hb by g. So g and g cancels. hb is 1, right? So it is root 4, that is 2. So x equals 2 meters. Okay, is the answer. A sphere of, next problem. A sphere of mass m rolls without slipping on an inclined plane. See, inclined plane, rolling in inclined plane. I've already discussed this in class. Okay, fine. I also given a video lecture, okay, on this thing. Inclination theta, find the linear acceleration of the sphere and the force of friction acting on it. Okay, what should be the minimum coefficient of static friction to support pure rolling? Okay, so it's direct formula. Okay, acceleration is given like this: g sine theta by 1 plus I by mr square, right? Okay. So here we get that A will be I for the solid sphere, it is 2 by 5 mr square. So g sine theta 1 plus 2 by 5, so it is 7 by 5. So it is 5 by 7 g sine theta. Okay, fine. And the frictional force acting on it. So mg sine theta minus f is ma. So what is f? Mg sine theta minus, put the value of a, 5 mg sine theta by 7. So it will be 2 by 7 mg sine theta, frictional force. Okay, so the minimum coefficient of friction, static friction to support pure rolling. So f must be lesser than equals fs max. We have direct formula for this also. Okay, I did that. Okay, mu s is It's like this. The formula was given like this. Mu s mean was tan theta by 1 plus m r square by I probably. Okay, let's see. So if you want to do this directly, we can also do this. So it is 2 by 7 mg sin theta. It is mu s n, so it is 2 by 7 mg sin theta than mu s mg cos theta. We know n equals mg cos theta in inclined plane, so it's gone. So mu s mean coming out to be 2 by 7 tan theta. Okay, and if you put this in direct formula, you can also get this same result. See, 1 plus m r square by 2 by 5 m r square. So m r square gone, it becomes 5 by 2. 1 plus 5 by 2. So it becomes 2 plus 5, 7. So 7 by 2. So it's 2 by 7 tan theta. Okay. Okay. Now let's do this problem. The sphere is on a rough mass is 0 polarized and sticks with it. Okay. Now this problem says this thing. See, here is a sphere, okay, of radius r. Now the mass of this sphere is capital M, say. Now a particle of mass small m is hitting it with velocity v0, okay, at a height h, okay, above the plane, okay. So it hits and sticks to it. This particle hits the sphere and sticks to it, okay, and this combined system starts rolling, okay, fine. So they asked you what is the linear speed of the combined system just after hitting, okay. So we have to conserve the linear momentum, because conserve linear momentum. As there is collision, we have to conserve linear momentum. So it is mv0, and say just after hitting the system, the velocity of the system becomes v, combined velocity. So it will be mv0 will be m plus m v, okay. So v will be mv0 by m plus m. Alright, the first problem is done, answer is done. The angular velocity is omega. So now they ask you to find omega just after the collision. Now conserve angular momentum. See, before hitting, the angular momentum about this center, it was, this height is h minus r, right? About the center, okay, it was h minus r, okay. So mv0 into h minus r, okay, the angular momentum about the center, okay, and it was, the sphere was at rest, so it has nothing. Now it is equals, after it hits, it becomes I omega, okay. So now it's very easy to calculate. I, we know, 2 by 5 capital M r square plus, this is a point object m, about the center it has distance r. So it will be mr squared simply. Okay, from the center it has perpendicular distance r. So about the center, about an axis from the passing through the center, the point particle small m is at a distance capital R, so it is mr square, the total moment of inertia of the system. We got it like this into omega. So omega will be mv0h minus r divided by r square 2 by 5 capital M plus small m. Okay, now they said find the value of h for which the sphere starts pure rolling. Okay, the mass capital M is much greater than small m. Okay, so we know for pure rolling it will be v equals omega r. Okay, v equals omega r, capital R. So how to do it? V we know, mv0 by m plus m we have calculated. Omega we have calculated mv0h minus r by r square 2 by 5 m plus small m into it will be r. Okay, now neglect this small m. Okay, so from here first let us cancel this thing. Let us simplify this as r. So we will get v0 also. So we will get 2 by 5 m capital R. I have neglected this small m. So it is equals, now also neglect this small m. We will get mh minus r. So cancel this m. Now we will have h equals 2r by 5 plus r. So it is 7r by 5. Okay, so this is the third answer. Okay. A cylinder is released from rest from the top of an inclined plane of inclination theta and length L. If the cylinder rolls without slipping, what will be its speed when it reaches the bottom? Okay, the first here this problem. Okay, so how to do this problem? We already know A is g sine theta plus 1 plus I by mr square. Now for cylinder, I is half mr square, so it will be A will be g sine theta by 1 plus half, so it is 3 by 2, so it will be 2 by 3 g sine theta. Now it's very easy. If it say it's theta, so it's rolling down this inclined plane from here to here. Okay, so it is covering a distance L with this acceleration. What will be starting from rest? The velocity here becoming v. So what will be v? It will be root 2L. So v will be 2 into 2 by 3 g sine theta into L. So it is 4 gl sine theta by 3. Okay. Now do the next problem. This problem, yo-yo problem. Okay. See, suppose the yo-yo is tied to the string like this, it is coming down with an acceleration, okay, a. So the tension in the string is T, the radius is R, and the weight acting is mg. Now it is coming down as well as it is rotating. So it is an example, this motion is a mixed motion. It is an example of mixed motion, translation as well as rotation. Okay, so আমরা যেভাবে করি রোলিং এর মতো মোশন, ঠিক আছে, সেভাবেই করতে হবে। উই হ্যাভ টু কনসিডার দ্য ট্রান্সলেশন অফ সেন্টার অফ মাস অ্যাজ ওয়েল অ্যাজ the rotation about center of mass. So the net force on this cylinder is mg minus t will be ma. This one is for translation, the equation of motion. Now for rotation it will be tau equals I alpha. Now tau is here, the torque is produced by tension, okay, so it's t into r, so half m r square alpha. ঠিক আছে, already I have discussed this type of problem in the class, okay. So I is half m r square for cylinder, so t is half m r alpha. So we know as there is no slipping, r alpha is a, so t equals half m a. Okay, now put this value here, we get mg minus half ma equals ma. So mg equals 3 by 2 ma, so this cancels out, I get a equals 2g by 3. Okay, so if the length of this rope is L, okay, so you see it is starting from rest, okay, so it acquires a velocity v, okay, after covering a distance L. So v will be, it is moving with an acceleration a, so what will be the velocity? V will be root 2al, so it will be root 2 into 2g by 3 into l, so v will be root over 4gl by 3, isn't it? So it will be 4 into 980 into 30 by 3, so it is being 3, so it is 4 into 98, let us write like this, 49 into 2, and this is 100. Okay, so v will be root 4 means 2, root 100 means 10, root 49 means 7 into root 2, so it will be 14 into 10 into 1.4, so 14 into 14 means 196 centimeter per second. Okay, this will be the answer. So the velocity will be v is 1.96 meter per second. This is the answer of this problem. Okay, see this velocity, okay, root 4gl by 3, it is independent of the mass and radius of this cylinder, yo-yo cylinder. Okay, see, fine, no m is there, no r is there. All right, okay, now let's do the next problem. So read this one. This system, okay, these two discs, two wheels connected by an axle, okay, this is placed on a moving truck, okay, the truck is accelerating, okay. So on this system a pseudo force will act, clear, because we know whenever we want to calculate from the frame of reference of an accelerated system, we must consider the pseudo force. Okay, so to do this problem, let me draw the free body diagram of a wheel. Okay, suppose the okay, let me draw like this. it will help you. Okay, a truck is there. Suppose a truck is there. Okay, it's moving. Okay, and this system is actually here. Okay, fine. So the truck is accelerating in this direction. Okay, say with a0. So here the pseudo force acts in the opposite direction, which is ma0. The friction must act in this direction because it is the friction that will produce the torque and which will rotate the wheel in this direction. Okay, so here we will get ma0 minus f is equals ma. Okay, a is the acceleration. Remember, a is the acceleration of the wheel with respect to the truck, with the respect to the reference frame of the truck. Okay, so here we will write now that torque tau equals I alpha. Okay, fine. So we will have tau equals I alpha means tau is Fr is I alpha. Okay, so here Fr equals, this is a disc, the wheel is a disc, half m r square alpha. So F is half m r alpha. Okay, now as the wheel is executing pure rolling, we must have pure rolling. Okay, we must have a equals to r alpha. Okay, as v equals r omega, a equals r alpha. Okay, fine. Okay, then we will write it as half ma. Okay, now let's put it here. We will get ma0 minus m minus f is half ma equals ma. So ma0 is 3 by 2 ma. So if I cancel this to m, okay, I'll write a as 2a0 by 3. So it will be 2 into 9 by 3. So a is 6 meter per second square. So they have asked you the frictional force. So F will be, you can put here F equals half ma, or from this equation also you can get whatever you like. Half into the mass of each disc is 2 kg. Okay, so it's 2 into a is 6, so it is 6 Newton. Okay, fine, this is the answer. Alright, okay, now let's do this problem, this one. Okay, so it is given that here is a particle, this is a disc. Okay, this is a disc. Okay, a particle is there attached to the disc and the whole system is rotating about this axis. Now this distance is r by 4. Okay, the whole system is rotating about this chord PQ. Now this is r by 4 and the radius of the disc is r. Okay, so mass of this point particle is m, so is the mass of the disc. Okay, m equal. So when this particle as the disk rotates. Okay, so we can understand that as the disk rotates, okay, so it will be like this. After 180-degree rotation, it will be like this, isn't it? Okay, the disk will be like this when it will be rotated by 180 degrees about this axis. Okay, and the point particle will come here. Okay, M. So when it reaches the bottom, the numerical asks that when it reaches the bottom, find the linear velocity of this mass. Okay, fine. So how to do it? We have to use the conservation of mechanical energy, but before that we must calculate the moment of inertia of the system. Okay, it will be interesting to calculate. So we know that the moment of inertia of the disk about the diametrical axis is 1/4 mr square, but we have to calculate it with respect to this chord. So we have to use parallel axis theorem. That means we have to do mr/4 square. Okay, so now this is the moment of inertia of the disk. Now what is the moment of inertia of the point mass? It will be m into r plus r/4 whole square. Okay, the distance of this point mass is r plus r/4 from the axis, so it is this. So it will be mr square by 4 plus mr square by 16 plus m 5r by 4. 5r by 4 means 25r square by 16. Okay, so it will be if I take mr square common, then it will be 1/4 plus 26 by 16. Okay, so it will be 16 4 plus 26, so 30 by 16. 30 by 16 means 15/8 mr square. Okay, so this will be the moment of inertia, okay, of the system of the disk and the point mass. Okay, here we have used the parallel axis theorem for the disk. Okay, this is the parallel axis theorem for the disk. Alright, now we have to just use the conservation of mechanical energy. Conserving mechanical energy. So it will be, see, the change in potential energy will be equal to the kinetic energy. Okay, so the change in potential energy is, it is now at a height of 5r/4. Okay, this, see, this point particle is a height of 5r/4. Okay, so when it will come down at the bottommost point, okay, so total change will be 5r/4 plus 5r/4, total change in height. Okay, fine. So mgh will be the change in the potential energy. Okay, so it will be, for the point particle, it will be mg into 10r/4. Alright, for the point particle. Now what is for the disk? Suppose the disk, the mass of the disk is concentrated at its center of mass, that is at the center. So it is at a height of r/4. Now when it will flip, so it will come downward at a height of r by 4. So the total change in height will be r by 4 plus r by 4, that is r by 2. Okay, so the change in potential energy for the disk will be mg r by 2. Okay, so this change in potential energy will be converted into the kinetic energy. So the kinetic energy can be written as half I omega square, the rotational kinetic energy. So we will have 5 by 2, so 5 mgr by 2, 6 mgr by 2, that is 3 mgr, and this will be half into 15 by 8 m r square omega square. Now see, it will be 3 5. Okay, m cancelled. Okay, so omega square becomes, this is r na, so omega square is coming out to be 16 g by 5r. Okay, so omega is root 16g by 5r. Now what they have asked you in the numerical, what is the linear velocity of this point particle? Okay, so this point particle is at a distance of 5r by 4 from the axis, so the linear velocity will be v equals to omega into 5r by 4, isn't it? So it will be root over 16g by 5r into 5r by 4. So root over 16g by 5r into 25 r square by 16. So 16 gone, so it will be r and it will be 5. So it is 5 gr. So v is root over 5 gr. Okay, fine.